What does a vector field have to do with rate of change? What does a vector field have to do with rate of change? Michael knows. Anybody else? Cody knows. Anybody else? What does a vector field have to do? Alexander knows. Brian knows. What do you think? Somebody knew. What's the relationship of a vector field and what does that have to do with rate of change? Ian, any idea?
No, I don't remember.
Okay. Josh, what do you think?
The size of the vectors in the vector field show the magnitude of vectors show how fast that point is increasing towards the highest point.
Okay. If the vector field is what? Yeah, so we talked about vector fields being gradient fields. So if a vector field is what? The gradient of some function, right? Then it's a gradient field. So gradient fields are like the derivative of a multivariable function, right? They're like the derivative of a surface. They're telling us direction and magnitude of rate of change. It's just maximum rate of change, right? So, okay, so they themselves, a vector field could be a derivative or rate of change, but what is the rate of change of a vector field? So if your vector field is your function, what's the rate of change of a vector field? You see how that's a different question? So we've talked about gradient fields as the derivative of a multivariable function. Now I want to talk about, vector fields themselves are functions in and of themselves, right? Given any point in space or in the plane, you get a vector. So when you take that whole thing, what can we talk about in terms of rate of change of a vector field? So that's what we're going to talk about today. This is a cool lecture. So it's called curl. Curl is what's called rotational rate of change of f. Rotational rate of change of f. So what we're going to do is we're going to investigate a small element of dA of a region D in a vector field PQ. So we're going to talk about curl in R2. So our vector field is PQ, are the x and y components of our vector field. We're going to investigate the little yellow element, right? I'm going to blow that up. So here's my element. dx is the horizontal dimension, dy is the vertical dimension of that element. So we're just looking at a little piece of a region in a vector field. Okay, and so then in the local area, we have vectors of the vector field. So I'm gonna say kind of just above our element is the top vector, and then below is the bottom vector, and then left and right. Right. So if you make a little change in x, across your element, so this is kind of how the vector changes, how the field changes this way. And then going this way, if you make a little change in y, this is how the field changes this way. Does it make sense? So we've got this element in a vector field, and we're looking at thinking about tiny changes and the resulting change in the vector field. So those are the kind of four surrounding vectors. Okay, so according to the right-hand rule, counterclockwise rotation is positive. So that's what makes curl greater than 0. Counterclockwise rotation makes curl greater than 0. So here are the components. Here's the horizontal components of those four vectors. Those are the p, right? Those are the p's. Horizontal components in the direction of x. And then we got the vertical components. Those are the q's, right? The direction of y. So I'm breaking up those four vectors now into their components, p and q. Does that make sense? So the question is, what components of the top and bottom vectors cause rotation? So which components, Q or P, cause this little rotation of this little element. Which vectors? Would it be the q vectors or the p vectors that would cause rotation of the element? What? No, it's not the angle. So some are saying both, some are saying p. What's going to cause rotation? Do the q vectors cause this thing to rotate, the q components? Do you see that they're just pulling vertically? That's not going to cause rotation. So we don't care about the q vectors. Don't miss this. Don't miss this. We don't care about the q vectors, right? Okay? When it comes to the top and bottom vectors, if we're interested in rotation, we care about what? The horizontal components, p. And so really what we're interested in, so the rotation is going to be caused by the change in p, right? So the change in p over a change in y. So down here, so as we change y, what happens to p? Does it get more positive or more negative as we change y this way? It's just in my little sketch here. It's increasing, right? P increases. Okay? So for a change in y, we want the change in p. The change in p is going to be this thing that causes rotation in terms of the top and bottom vectors. Okay? And so what do we need then? If I know what the change in y is and I want the change in p, what do I need to calculate the change in p?
The change in p with respect to y.
Right. The rate of change, right? I want the rate of change of p with respect to y, the partial derivative. So the partial derivative with respect to y, of p with respect to y, is going to allow me to get that change in p for the given change in y. And that change in p is going to help me determine how much rotation I have. Do you see that? Now, is this change in p going to give me positive rotation or negative rotation? Which way is the direction of positive rotation? Counterclockwise. So if I have a bigger p on the top than the bottom, which way is that going to cause it to turn? Clockwise. Do you see that that's going to be clockwise? Then the change, if p is increasing for an increasing y, that's going to cause clockwise rotation. So this is going to, this situation will actually be a negative curl. Okay. What about the left and right components? So what about the left and right vectors? Do we care about the p's or the q's in terms of rotation? Now we care about the q's. The p's are just going to pull and push on this thing. It's not going to make it rotate. But the q's will make this thing turn. Do you see that? Okay, so all we care about then for that is the q's. Now I'm showing it, same thing. So if I've got the change in x, and I want the change in q is going to help me get the rotation, then what do I need for that? I need the partial of q with respect to x. That's what's going to give me my change in q for a given change in x. And now what about this? For a positive change in q, does that make a positive curl or a negative curl? So I'm showing a positive change in q, right? This is bigger. This is bigger than this. Is that going to cause counterclockwise or clockwise rotation? Counterclockwise. So it's going to cause counterclockwise rotation. So a positive change in q is going to correspond with a positive curl. So then we're going to put those together now. So we want the effect of the change in p together with the change in q is going to give us the total rotation. Do you see? So what was the effect of q? Was positive, right? But the effect of p is opposite, right? A positive p gives clockwise rotation. So when we put it together, we want to do this. We want to take the rate of change of q with respect to x minus the rate of change of p with respect to y. And that's going to be my total rate of change in the counterclockwise direction. Or in other words, qx minus py. That's giving me my rate of change, my rotational rate of change in the xy plane?
Okay.
Yeah, so you recognize that?
Yeah.
Right? So this is what? Rotational rate of change. Rotational rate of change. And if positive is counterclockwise, then we want qx minus py. And that's the curl of f. That's the curl of f. But have we done curl before?
No.
No, okay. Okay, but curl is a vector, okay? So curl is a vector. So what's the direction of the vector? What's the direction of the vector if curl is a vector, giving us the rate of change around a counterclockwise loop? What would that be? No. So this is like when we did, we've kind of done this before. When did we do this? Like twisting, remember? Twisting the wrench, right? So twisting the wrench.
Would it be out of the page in this?
Yeah, so it's the right-hand rule. So counterclockwise rotation is going to be, give us, the direction is actually k. So the direction of the curl is actually orthogonal to the plane of rotation. So the curl of f is, here's the magnitude. The magnitude of it is qx minus py, and the direction is going to be k, because rotation about the direction of rotation is all orthogonal to the plane of that rotation. Does it make sense? So we're talking about rotational rate of change of a vector field is a pointwise phenomenon that's telling us the strength of rotation at every point, the strength of counterclockwise rotation at every point. So it has to do with what? The horizontal components of the vectors, above and below for a change in y, and the vertical components of the vectors for a change in x. Those are the ones that contribute to this rotation.
Is this in any way related to curvature?
Probably somehow, but curvature is not now, because this is for a vector field and curvature is for a curve. So it's two different kind of mediums there. But there might be something related. If you had a path through a vector field and you were calculating curvature and the effect of the vector field, there probably is something in there. Okay, any questions on this? Okay, but we want to do curl in R3. Well, we've already kind of taken care of some of that. So now in curl in R3, we're going to investigate a small element dv in a solid E. So now we have some solid E, and then we have little dv's. Okay, and so I'm showing you a dv, and this didn't really turn out here. So let's do. Yeah, so this is, I don't know if you can see that. So when you're talking about that, so now there's actually rotation relative to three different planes. The rotation relative to the xy plane we've already done. So that would be like looking down. Is that right? Is that right? Y? No. Looking down, like over here. Looking down on our elements. I got x to the right and y this way. That's the case we just did for R2. Okay. So we've already done that. So then there's two more aspects to rotation based on the other two planes. So let's investigate the YZ plane. So here I have the element. I'm looking in our standard view here, and I've got Y is to the right and Z is up and down. And then here are the vectors, the vectors around it in parallel to the YZ plane. Okay, so our vector field is PQR. So here are the. So I'm going to get rid of this. Get rid of this. Distracting. Can you kind of see the faint lines now that I've drawn them? I still imagine that's a little dV, barely. Anyway. All right, so here are the 4 vectors we're interested in. And so now for show that. Okay, so let's do green. What are the horizontal components of these vectors? P, Q, or R? Horizontal components. Are they P, Q, or R? A couple of people are saying Q. Do you agree with that? Yeah, they're the Y components, right? Because we're looking at the YZ plane. So this is my QT, and this is my QR, and then my Q bottom, and my Q left. All right, what about the vertical components of these vectors? P, Q, or R? Well, P or R? These are R, right? These are the Z components. So I got R top, R right, R bottom, and R left. So it's the same thing as before. So for a change in Z, we care about what components of the top and bottom vectors. For a change in Z, we care about Q, right? We don't care about these, right? So for rotation, we don't care about that one. We don't care about that one. And then for a change in Y, we care about what components? For change in Y. We care about the R's now, right? We care about the R's for change in Y. We care about the Q's for change in Z. So we don't care about these. And it's going to be the same thing as 4. So what will the rate of change be? The rate of change of Q with respect to Z, right? The rate of change of Q with respect to Z, and that will be positive or negative for positive curl? Negative, right? Because a positive change in Q will turn it clockwise. So we want the opposite of the rate of change of Q with respect to Z. And then for a change in Y, we want the rate of change of R with respect to Y, and we want that to be positive or negative to get positive curl. Positive, right? Because a positive change in R is going to give us the counterclockwise rotation that we want. Are you following this?
Are we looking at just one side of R changing, or both sides are changing?
The change in R is across a change in Y, right? This is a one vector here, and then if you make a little change in Y, you have a slightly different vector that has a change in R. So it's the change in R from here to here. You understand? It's the change in R across a little change in Y. And then the change in Q across a little change in Z. So those rates of change will determine the strength of rotation. And we want the we said Q with respect to Z, and what? We want the positive R with respect to Y, and we want the negative Q with respect to Z to get it all in the counterclockwise, right? And then what will the direction of, as a vector, what will the direction of this be? So that's in the parallel to the YZ plane, the rate of change
Would be inside the plane, or inside the pole?
Parallel to the x-axis.
Right, so right-hand rule makes it be what direction? X direction, right? So it's going to be times I. So in terms of a dV, like the rotation dV, we got 2 of the 3 done, right? So it's going to be the combination of rotation parallel to XY, rotation parallel to YZ, and rotation parallel to XZ. Okay, so we won't do the geometry of the last case, but we're going to show the algebra of it now. So when we talked about right-hand rule, that goes back to cross product, right? So curl is really about cross product. So here's how we compute it algebraically. We make a matrix of the unit basis vector. So you got unit basis vectors, that's your top row. And then this is like operation, right? So this is take the partial derivative. They're not quantities in themselves, so this is like what we call the gradient operator. We're not going to be actually multiplying when we do this determinant. We're going to be, that is telling us to take derivatives. So we call that the gradient operator, and then here's our vector field. So when we do so this is that gradient operator right there. And so we're gonna follow the cross product algorithm, but with a gradient operator, meaning take these partial derivatives p, q, and r with respect to x, y, and z as we follow the algorithm for cross product, or yeah, for determinant. Okay, so what will it be? So I will be what? The partial of r with respect to y minus the partial of q with respect to z. Is that the one we just did? That's the one we just did in the previous screen. Remember that? So when you follow the cross product thing, you get the partial of r with respect to y minus the partial of q with respect to z. And then what about k? That was the one we did in the first screen when we did r2. Partial of x with respect to, partial of q with respect to x minus partial of p with respect to y. That's what we said, right? So then the one we didn't do would be parallel to the xz plane. And what will that be? That'll be the partial of p with respect to z minus r with respect to x. So you go down, positive down to the right, negative down to the left, right? So going down to the right, this would be a p here, so partial of p with respect to z. And then going down to the left, this would be r with respect to x. And then when you add all those three contributions of rotation together, you get the whole curl of the vector field at that location dv. So this is the curl. This is the curl of f. This is the rotational rate of change of a three-dimensional vector field. It has components relative to the xy plane, yz plane, and xz plane. Okay, so then the magnitude of the curl is the strength of this rotational rate of change, just as without direction. And then the direction of the curl is orthogonal to the plane of rotation. So when you put the three together, so at a particular point, there's only really rotation in one plane, but it's going to be like an oblique plane, right? So adding the three components together give you rotation in some oblique plane. And so then the overall direction of your curl is orthogonal to that oblique plane. But this is breaking it down into components parallel to our coordinate planes. But when you add it all together, you really just get rotation in one plane, but it's going to be like slanted compared to everything else because you're adding all the components together. And then you have a particular direction of the curl which is orthogonal to that plane. Does that make sense? Okay, here's the big takeaway though. Curl is a function. Rotational rate is a pointwise phenomenon, meaning as soon as you move to a different place in the field, it changes. And when we're calculating the curl, you're calculating rotational rate of change at a particular point in the field. And that's a function, right? So given a point, you have a curl. Given another point, you have a curl. Given another point, you have a curl. Given another, so at every given point, there is some value of curl, and so that can change throughout the field. So, do you get that? Do you really get that?
What is this trying to tell us about the field? Just like a visual type of.
Yeah. So like at any point, it's the rotational, it's the strength of rotation, right? Strength and direction of rotation at any point in the field. Tendency of rotation.
So does that tell you it wants to go this direction next?
We're about to kind of investigate that. Yeah, we're about to investigate that. That's the right question. Okay, so here's an example. We'll do a couple, this is R2 example. So here's a field, here's a vector field. And so, is the curl positive or negative? Is the curl positive or negative? Positive. Why is it positive? Because we're going counterclockwise, right? We're going counterclockwise. Well, let's take a closer look at that. So let's just pick a point here. I'll pick a point like right here. Okay, so when we look, as we're changing in the x, I'm going to draw components here of these vectors around that point. So I'm interested in that point right there. Okay, so as I draw these components going up, what happens to, I guess these are Q's, right? Or these Q's are like that. So what kind of rotation does that indicate, right? So above or below, I have my horizontal component below is bigger to the left than the one above is smaller to the left. What kind of rotation does that indicate? Clockwise or counterclockwise? This one down here is bigger than this one.
Oh, wait, no.
Clockwise, right? Okay. And so now I'm going to look at the just blue. Now I'm going to look at the vertical components. So what's happening to these vertical components as I go to the, those are getting smaller. So the one over here, can we just assume it's bigger? I don't have a vector right now there, but no, I kind of picked a bad spot. Let's pick a better spot here. Sorry, we want to pick a spot like over here. That's better. All right, so still we got the. These are getting smaller going up, right? Let me see that. And then now going this way, that one's bigger than this one's bigger than this one. Okay, so now on the so in terms of left to right, so my one on the left is bigger up than my one on the right. Which kind of rotation does that indicate? Clockwise or counterclockwise? So, uh-oh, I thought you said this was positive curl. When I look at vectors above and below, it indicates clockwise rotation. When I look at vectors left and right, it indicates clockwise rotation. Is the curl positive or negative? Curl is positive or negative? Negative. What happened to, it's positive because the whole thing is swirling in a counterclockwise direction. No?
You said it's point-wise, so it's going to change depending on where you are.
Right, that's why I asked you if you really believe me when I told you that curl is pointwise. Do you really believe me that curl is pointwise? It's not about the whole vector field swirling in a counterclockwise direction. It's about what's happening at every individual point. And even though the whole thing is a big whirlpool going this way. At any given point, you have clockwise rotation. So what you want to think about is like if you had a little flywheel in your vector field like this. What do we care about the flywheel if we're concerned about curl? What do we care about the flywheel? Which way it's spinning, not which way it's moving, right? If you just let it move, how's it going to move? It's going to move in a big counterclockwise circle, but as it's doing that, what's it going to do? It's going to turn clockwise, and which is the curl? How that thing is spinning, how that thing itself is turning, because it's just what's the rotational strength at that given point. So, yeah. The point is still taken. All right, so it's swirling counterclockwise, but that's not what determines the curl. The curl is determined by pointwise. It's a pointwise phenomenon. So the flywheel will spin clockwise, and that's why the curl is less than 0. All right, another example. So I'm confusing this example with the next one. That's why I'm stuttering here. A sec. Okay. So here's another one. So what do you think about this one? So it also has the idea of what? Counterclockwise rotation. What do you think about the curl of this one? What do you think about the curl of this one? So this time we're going to do the math. So for this one, I'm going to do the math. Here's the vector field. So what do you think? Do you think it's positive or negative? All right. Who knows? Just the fact that it's twisting in the counterclockwise direction is not why it would be positive. Okay? So it's a pointwise phenomenon. So now we're gonna practice, and you're actually going to compute the curl for this vector field. So that goes back to that determinant algorithm. Remember, I, J, K, and then partial with respect to x, partial with respect to y, partial with respect to z, and then our field, negative y, x to the minus 2, x to the minus 1, 0. And when we take the determinant of that, that's going to give us the curl. So the curl of this vector field, rotational rate of change is, so I component, so the partial of 0 with respect to y minus the partial of this with respect to z. So what's that? 0, right? Partial of 0 with respect to y is 0. Going this way, partial of x to the minus 1 with respect to z is 0. There's no z's in it, right? X to minus 1. Next one. J. Partial of that with respect to z. What's that? 0. Going this way. Partial of 0 with respect to x. 0. Now the k components. Partial of x to the minus 1 with respect to x. So negative x to the minus 2 minus partial of this with respect to y. Negative x to the minus 2. And remember what this was? This was qx minus py. That was our z component. Remember that? Qx minus py is our z component of the curl. What's the curl? What does that mean? It's 0. Qx minus py is 0. What does it mean? Okay, I heard it's a gradient field. Right, it's a gradient field. What does it mean for a flywheel? It's not going to spin, right? It's just going to move around. It's It's just going to move around in a circle. It's going to move, but it's not going to spin. So when the curl is 0, the field is called. So what about the curl is called? Curl equals 0 means the field is irrotational. This big whirlpool is an irrotational field. Why is it an irrotational field? Isn't it rotating in a big circle? But at any given point, there's no tendency of rotation at all at every point in the field. Even though the whole thing moves in that direction, if you're sitting on the flywheel, you would not be spinning at all. You would just be cruising around in a circle. And so if a field is irrotational, some people are saying it, what does that mean about the field? Yeah, Qx equals Py, right? It's a gradient field. Gradient fields, we can add this to the list, right? We had a list of all those things about a conservative vector field. So we have a new thing to the list. A conservative vector field is irrotational. Okay, irrotational. There's no tendency of rotation anywhere in the field. Okay, so just because the whole thing has a macro or a global rotation has nothing to do with the curl. So a big whirlpool could have positive curl, it could have negative curl, it could have 0 curl, or it could vary in the field, right? So at different places you could have, the whole thing could be turning in one direction, and in some places you could have negative curl, and other places you could have positive curl and 0 curl, etc. Okay, well, so I asked at the beginning of class, I said, what's the rate of change of a vector field? So what's the rate of change of the vector field, of a vector field? Curl. But actually, that's only half the story. There are 2 rates of change of vector fields. There's another kind of rate of change, and it's easier. We can do it in 5 minutes, okay? It's easier. This is the second kind of rate of change of a vector field. It's called divergence. Divergence is the tendency of expansion or contraction. It's the tendency of, or the strength of expansion or contraction. So same thing, I'm going to investigate my little element. And I've got my P and Q components. So above and below, which components will contribute to expansion or contraction? He's saying top and bottom are vertical. That's right. So I kind of drew that in a bad place. It's better to draw it right here in the middle, right? So draw this vector over here, and that's my Q. That's my Q, Q, Q. So for a change in Y, which vectors contribute to expansion or contraction? P or Q? Q. And for a change in X? P. But those are the direct, so Q is in the direction of Y, and P is in the direction of X. That's why this makes it a lot easier. Okay? Oh, there we go. So for a change in X, we want the change in P. That's going to be the partial P with respect to X. And for a change in Q, it's going to be the partial Q with respect to Y. So the total rate of expansion for let's just jump right to R3. It's just going to be the rate of change of P with respect to X plus the rate of change of Q with respect to Y plus the rate of change of R with respect to Z. Because the components of expansion are in the same direction as they're parallel to those changes, right? Or Px plus Qy plus Rz. This is called the divergence. This is called the divergence of F. What direction is divergence in? What direction is divergence in?
Is it just outward?
Which way is outward of a solid? So instead of using the cross product of the gradient operator, now use the dot of the gradient operator. And dot products don't have direction, right? They're just magnitude. So when you add together these partial derivatives, you just get a value. There's no direction associated with expansion or contraction. So we're still using that gradient operator, see that? But we're gonna dot it with the vector field, PQR. And that's gonna result in this formula here. Partial of P with respect to X plus partial of Q with respect to Y plus partial of Z with respect to R. Dot product algorithm. Doesn't make sense. So let's go back to that field that we were just working on. This one. And let's predict. We're going to look at different quadrants here and predict. So in the direction of motion, so for divergence, you have to look in the direction of motion, and then you have to say, are you getting squeezed in, or are you getting more room, right? So looking in the first quadrant here, as we're moving kind of up and to the right, and as you move up and to the right, are things opening up, and we can breathe more, or are we getting squished in as we move up and to the right along with the vector field? But these vectors have greater magnitude than the ones that were coming. So our vectors are increasing in magnitude as we move in that direction. Expansion or contraction? Expansion. So in the first quadrant, divergence of F is greater than 0. This way, moving down and to the left, negative. Down and to the right, positive. Up and to the right, negative. We're getting crunched together, right? So let's see how that comes out in when we do the divergence of this field. So the divergence of the field is partial of this with respect to x would be negative 2 times negative y over x cubed. Is that right? Plus partial of this with respect to y is 0. Partial of this with respect to z, 0. So the divergence is also a function, also a pointwise phenomenon. Positive 2y over x cubed for this field. That's what the divergence is. In the first quadrant, will that be positive or negative?
Positive.
Both x and y will be positive, so we'll get positive. That's what we said, right? We said it was positive in the first quadrant. Second quadrant, x's are negative, y's are positive, therefore negative. That's what we said. See? Third quadrant, x and y are negative, so we're going to get a positive divergence. That's what we said. It's expanding in the direction of motion. Fourth quadrant, positive x, negative y makes negative, and that's what we said. In the direction of motion, we're getting crunched together. So it's a pointwise phenomenon. There is a tendency of expansion or contraction at any given point in the field. It's a function of location.
So you had like a balloon that could only withstand so much, and then it managed to exceed that with divergence for the balloon pop.
I'm not sure.